Hello everybody, how's it going? Welcome to the Car Hacking Village. Is this working now? Am I streaming? Cool. So welcome everybody. As you've seen, with the essence of everything going on this year, we tried to build the Car Hacking Village in Robert's garage, so that's where we're at right now. We do have a Tesla here that you guys are more than welcome to hack. We've got a truck over here as well, and there'll be more details on that coming soon. A lot of that's going to be through our CTF and through our challenges. Kind of going over the breakdown of how our village is set up this year. We will be operating from 10 a.m. to 5 p.m. Pacific Standard Time, Friday, Saturday, and then on Sunday we'll be going from 10 a.m. to 12 p.m. or 12 p.m. Pacific Standard Time. Our CTF environments, we plan to have those up and running as much as possible. We do have a lot of our staff in different areas around the world, so things might be going up and down depending on their time zones and whether they're asleep or awake. So for access to CTF stuff, there's certain channels on Discord for that. If you need help getting access to our CTFs, if you need help getting into our CTFs, whatever it may be, please go to those channels. Our CTF admin, his name is Uberwoozle on Discord. So please reach out to him if you have any direct issues or problems. He can help work those out. A couple other things we're going to go over is really kind of how Discord's laid out. So we have our Discord set up where we have lounges, we have hangout areas, we have support channels, we have a lot of different areas to help people understand what they're working with. So for instance, all of our talks will be through different track channels. So a lot of it, we're working to get it streaming on Discord, but we're having a little bit of technical issues right now. But everything is streaming on YouTube, Twitch, and Facebook. So you should be able to see all that right now. It is, the information's live on carhackingvillage.com if you do want to be able to get to any of those links. But when we get to Q&A after the talks, the plan for that will be and ask your questions in the text area of whatever track that talk was in. So if a talk is in track 1, you'd want to join CHV Track 001 text and ask your questions in regards to that talk in there. And then we will have an MC standing here as well as the speaker on audio and Discord. That will be answering those questions, and we'll be filtering through the chats as well to make sure we get your guys' questions answered. So if you have any questions on that, just feel free to throw something in general on Discord. If you're curious on how that works, I can help you guys understand that a little bit better. And most of the details are on our website. I think there's a few things I have to work on updating, but most of it is there and broken down. So detailing more about talks, all our talk schedule is posted on our website. We've also been hitting up Twitter and a few other areas, so you should be able to get access to our schedule pretty easily, and all the links are directly there if you want to see any talks. We do plan to get these talks to DEF CON after the conference, so they will go on their media servers, so you guys will be able to have access to this content after the conference as well. So yeah, back into CTF stuff. The way that's broken down a little bit this year, we have a CTF, like I was mentioning earlier, with challenges and the ability to hack these cars and a lot of different components that are all around the world. We also have a one-on-one section that we created this year, which we're calling CHV 101. The whole point of that is if you don't really understand car hacking or you're just trying to get into this industry or this field, there's a lot of different staff that can help you guys in those areas. And we've also set up a bunch of different like basic car hacking talks for you guys to kind of understand the basics of getting into cars and what areas might be interested to hack. So those talks will be streaming on different channels. I think I still need to get those links put up on the website, so I'll work on getting that set up here pretty soon. But that'll all be available. The way the schedule's working is we're running the same thing on Friday and the same thing on Saturday. So if you're busy with something else today, then maybe you can try to catch a talk tomorrow. We will have a similar Q&A style on those, like we do with the main talks. So our Discord is set up very similar, where if you have questions, there's a CHV 101 talks text channel. Please put your questions in there, and they will be answered via the voice channel by the speaker and a moderator. For CTF still, our prizes this year, for those that haven't seen it yet, Our third place prize will be for an Oculus Quest. That's in lieu of Craig Smith's VR Trunk Escape Challenge. So we thought it'd be cool to include something VR related. And anybody that has questions on the VR stuff, please reach out to Craig for that. Our second place prize will be an Automotive Hacker Toolkit. We're still working to post the details, so we'll post them pretty soon. It'll more than likely include a badge, Car Hacking Village badge or two, which are essentially automotive Ethernet hacking tools, as well as a whole set of different tools as well. And then our first place prize will be a fully paid trip for two to DEF CON 29. I think in essence of us all not being able to travel or do anything, it'd be nice to get somebody out there and be able to kind of pay the whole trip ahead. So that's how the CTF prizes will be working out this year. We will be doing a closing ceremony on Sunday. I believe it's at 1 p.m. Pacific Standard Time, and that's when we'll announce the winners and essentially how everything was handled during the event. And then the last thing for CTF, if you do need access to different platforms, they're also listed on our website. We have a scoring engine, so you'll have to log into the scoring engine to be able to start seeing the challenges. That should be set up through Discord, so you should be able to just log in through Discord. You don't have to create an account or anything. And then we also have a virtual Car Hacking Village website where we're actually hosting all the different components that you guys are able to hack. And there'll essentially be a web-based TMUX terminal that you can get access to start hacking the Tesla, the truck, all the other devices that we have available. And that's about it. So in a few minutes here, we're going to start streaming some talks. We'll get the first talk going, which is, I believe, Powerline Truck Hacking by Ben Gardner and Chris Poor. So in a moment here, we'll have an MC come up and kind of give more details and background about them, and then we'll get the talk streaming through YouTube, Twitch, and Facebook. Thanks again, everybody. Welcome to the Car Hacking Village. We hope you guys have a wonderful time. Have a good one.
Hello, no one is available to take your call. Please leave a message after the tone. Hello, no one is available to take your call. Please leave a message after the tone. Hello.
Okay, time for the next talk. This next talk is before J1939, a J1708 and J1587 protocol decoder. The speakers are Dan Salloum and Thomas Hayes. Daniel Salloum is a reverse engineer by title and curious at heart. He is currently employed by Assured Information Security, where he spends his days doing security evaluations and creating tools that help. His background as both a system admin and programmer help him to navigate system innards. If it must be done more than twice, he'll script it. If it can be created in a few hours, it probably will be. Daniel has recently been accepted into the world of ham radio and may be heard on the airwaves at some point. This is his first conference and expects it won't be the last. Thomas Hayes is a hardware engineer at Bendix Commercial Vehicle Systems in Elyria, Ohio, and a member of the SAE J1939 committees. In his current role, he manages the hardware process for braking and other heavy vehicle systems, from brainstorming with napkin drawings to the creation of full PCBs to product testing and manufacturing. Prior to Bendix, Thomas held design and leadership roles in a number of venture-backed startups and worked in simulation technology for the aviation industry. In his spare time, Thomas enjoys rebuilding vintage motorcycles and teaching kids how to solder without burning their fingers off. Success rate, unknown. So during the talk, make sure to take a look at the CHV Track 2 text, and the talkers should be available in there. The speakers should be available in there for questions and answers as we go. So let's cue it up.
Hi, everyone. Today, I'd like to welcome you guys to Car Hacking Village of DEF CON 2020 Safe Mode. Today's presentation is going to be a throwback to the times before J1939. If you don't know what that is a protocol that runs on top of CAN and is primarily used in heavy vehicle component communications. So we will be talking about how we came about the creation of a decoder / parser for J1708 and J1587. So just a quick breakdown of how this presentation is going to pan out. First, we will let you know who we are. We're going to let you know how this project came about. And then we're going to give a brief recap of the protocols that are interesting to us. And you will then see how we came across these protocols. Afterward, we're going to talk about the decoder / parser, and we'll give you a quick demo. Last, we'll conclude this talk with the info you'll need to pick up where we are leaving off. Okay, so my name is Daniel Salloum. I'm a reverse engineer at Assured Information Security. We're based out of Rome, New York. I've been with them for a little over a year and a half at this point. And I spend my days analyzing the security of things, digging into protocols, and developing anything to support these efforts. You can see in the images, I'm on the right-hand side, and there's an image of Thomas on the left-hand side. So now you have proof that we actually work. So.
Hi. So my name is Thomas Hayes. I'm a hardware engineer at Bendix Commercial Vehicle Systems based out of Elyria, Ohio. I spend most of my days designing hardware, so PCBs and digital and analog interfaces for brake control systems. And I've been there for almost 5 years now.
Okay, so what are we doing here? Well, we discovered that there are more than just J1939 messages that cross the networks in heavy trucks. And within this traffic, there's some very interesting data. So we're here to show you how it came about, as we needed a simple way to see it. And I can imagine you guys want to see how the decoder works as well.
So is there a backstory? We know trucks, I've been playing them for a while. This project started off in mid-2019 when we started to do some exploratory testing on heavy vehicle systems. We notice multiple networks and the interconnection between all of these modules. We start to explore some tools and decoders that are already out there available for use for people in industry. And these legacy protocols, so J1708 and J1587, are still being sent across the bus, even though now the CAN J1939 is much more prevalent in newer vehicles. And it looks like it could be very interesting, as it is a very important bus that happens on the vehicle with a lot of useful information that we were interested in looking at.
Okay, so how do we, what do we need in order to get things rolling? First is an understanding of the protocols involved. In this case, we mentioned J1708 and J1587. They kind of work together. We also need a hassle-free way of analyzing the traffic that we see. And at that point, we can decide what may or may not be done with this data.
So what are J1708 and J1587? So they are SAE, the Society for Automotive Engineers, standards for medium and heavy duty vehicles post-1985. J1708 describes the physical layer and data links layer and defines a bidirectional serial vehicle network. So J1708 defines how the messages are structured and how they're distributed over the network. And 1587 makes up the transport application layer and describes messages, format, and parameters. So that's almost a big dictionary for all the possible messages that can be sent over this communication protocol. So 1708 is almost always used in conjunction with the application layer protocol, J1587. It's based on an RS-45 bus. We can have a max of 20 nodes on a vehicle, and it runs at 9600 baud. A message contains a one byte long MID, a message identifier, followed by some data related to that MID, and a 1 byte checksum. The message can be up to 21 bytes long. However, if the vehicle is stopped and no movement is detected, the messages can be longer if required. So J728 MIDs, we go up to 0 to 127, defined by J1708. And these are defined by SAE for important vehicle systems. And then from 128 to 255 are defined by J1587. And these are used a little bit more for maintenance and information on the vehicle, more from a diagnostic side. It's very cool. The MIDs also serve as an arbitration method for the communication. So the lower your MID number is, so let's say 0 to 7 for engine, that means it's a very high important message and will be passed before perhaps the trip recorder message with an MID of 56 to 61. The checksum is quite simple. It's a 2's complement of the sum of the message, and the data content is defined by the applications document given by the supplier. So you can send the messages defined by SAE, or possibly something defined by you as a manufacturer if you need to send something specific or proprietary across the bus. So J1587 defines the PID, the parameter identifier. So that's a little bit of a complement to the MID. So say if you have an MID for the engine, a PID can be related to your engine oil or a knock sensor or something in your camshaft. So it's a little bit more information for the PID for the system to recognize if there's a fault and direct where that fault can be. So it consists of one MID, one or more PIDs, and a checksum. The data length for 1587 message is mostly limited to 21 bytes, according to J1708. And if a message needs to be longer than 21 bytes, we can use the COTS, the TP4. So that can be used to segment and reassemble large messages if needed. And a lot of the PIDs are standard. So the PIDs range from 0 to 4 bytes. And the units resolution range will be defined in the spec or by whoever is sending them out. So if you're one engine manufacturer could say the PID for oil pressure is 1 PSI per bit, or another one could say it's 5. So it just depends on the manufacturer for that PID. There's also SIDs. These are related to the MID, but these are more related to anything that can be used to identify a section that is not necessarily covered under a PID, but covered under a diagnostic MID. So the MIDs for using SIDs will begin at 128, as defined by 1587. And these are really used for something that can be troubleshooted or replaced by a field technician if needed. So what's in the data? Now, a lot of our testing was in the communication between trucks and trailers. So the trailer has an ABS ECU, and the trailer also has an ABS ECU, and those two will talk to each other using this protocol. The trailer ABS can have all kinds of diagnostic message. A chuff test is a test of the system. It will modulate the air solenoids a little bit and dispense a bit of air. Like when you hear a truck brake, you hear a large air release sound, and that's kind of just making sure that your system's working properly. You can restart the ECU, you can check the status of the ECU, and most importantly, demonstrate an ABS fault. So as per SAE standard, the ABS fault, if the trailer has an issue, the trailer ECU has to communicate to the truck ECU and illuminate a light on the dash, as well as a light on the trailer itself, indicating that there is an issue with the ABS and it needs to be resolved. Diving a little bit deeper, there's also configuration options on the ECU. So wheel size, which then relate to the speed of the vehicle, as there's a tone ring that counts the amount of rotations done, and driver info, so where the trailer is going and what truck it is connected to at the lot, and sensor data. So it's the speed, mileage, your odometer stored on the ABS, trailer ABS, location, temperature, and many proprietary vendor messages. So who uses J1708 and 1587? So any kind of heavy vehicles that we all know, but also school buses follow that same platform, military vehicles, and we even found that yachts will be using the same communication platform. So our use case, we were observing exchange between a tractor and a trailer. They, as I said, the brake controllers communicate over J1708 and J1587, and these messages actually pass over a power line, which is very cool. Trailer manufacturers did not want to add another wire or two needed for an ABS communication. So they superimpose a sinusoidal wave on the power line going from the trailer, which then gets filtered out on the trailer side and on the truck side, depending if it's using that communication. It's very cool, but Dan and I did not focus our time on this. We were working on the J1708 and J5780 protocol.
Okay, so the question comes up now, how do we look at these messages? There's a couple of options. We can use tools that were developed for J1939 and are backward compatible with the other two protocols we mentioned. Or we can get our hands on an RS-485 transceiver, some bubble gum, a paper clip, maybe a tinfoil hat, and see what we can hack up. But what happens when our bus is a power line? In this case, you need a specialty diagnostic tool. Some of the larger companies like Nexic, Haldex, DG Tech, they provide these. But the problem with this approach is it's going to cost you some moolah. And flow between programs is not really there, as the software is kind of tied with the hardware and it's all proprietary, which means minimal flexibility. So our solution is Pretty J1587. This is a decoder that helps with at least part of the problem. By default, this takes in hexadecimal bytes, which are comma delimited, but really it can take in a stream of any bytes, and a user can define how to manipulate that data to be parsed correctly by the decoder. It also supports reading from standard in files or sockets, UDP or TCP. And what it does is it takes this information, these messages, and it will break them down into a human tolerable format, so they can be easily analyzed by an end user. So to start off, what happens is the parser will read the SAE documentation PDFs. Okay, and it will do this to set up a primary database, which is used for interpreting the data that's coming in. And this is needed because there's no simple database holding the data that we need in a convenient format. Okay, it's all in the specifications or proprietary by vendors. So there is an option for an end user to create custom messages with this tool. And this will be handy for working with proprietary data. The benefit of this, using this tool, is that it can be piped from or to other programs, as it's just a command line utility. So there are some requirements. What do we need to get this off the ground? Well, the first part is on you guys. You're going to need an interface to some bus to get the traffic. The next part is it uses the program PDF to text, which is contained within the popular utils package standard on most Linux distributions. Okay, and what happens with this is we use this tool to convert the SAE portable document format specifications into formatted text files. Okay. Then you need Python 2. We are hoping to port this to Python 3, but it started as a spaghetti code project that we just needed up and running, and Python 2 was default here, and that's what we stuck with until now when we realized it's actually useful. There's still some minor issues with it. The spec obviously was not written with being parsed in mind. Okay, so there's a lot of regular expressions and things that parse this information out of these files. Okay, so I think at this point, I'm going to give you guys a quick demo about how this thing works. It's a repository which will be made public after this talk. And you can just clone it, and at that point, you will set up the configuration file to point at the text files that you've created from using PDF to text on the SAE J1587 and 1708 specifications. Okay, so the first thing that I'll mention is this repository. Within it, we have a tool called Fuzzy Messages, which I'll be using for the demo. All right, this program just creates random bytes, I believe 1 to 19 bytes in length. And this winds up working out as a nice test environment to create a robust program. That way it's not just failing on any sort of messages. As you might see when running different types of hardware, you'll get funky bytes that aren't actually part of the message at times. So we've decided to make this program a little bit robust, and that it won't just error out on an incorrect message. It might print a warning to standard out, and it'll keep chugging. Okay, so the first thing I'm going to do is I'm going to create a file with, let's say, 100 messages, and I'm going to write that to temp. Okay, let me just make sure that that worked. Yep, seems like I got messages in there. All right, so now to run the tool, I just point it at that file that I created with all the messages. I'm also going to give it a flag to print delimiters between the messages. So you can see when there are errors, it gets printed to standard error. So these could be piped to dev null if you're not interested. But you can also see here the original message, MID in hexadecimal, and these also are accompanied by decimal forms. And then the PIDs and the meanings of the PIDs along with the accompanying bytes. Okay, so that's pretty good. But if you want more information, you can give this program a little bit more verbosity, like so, and you'll get details. This is the same message here that we saw previously, but now you could see it's giving details about the individual bytes related to a PID. So here we can see there's 1 byte, and this has to do with the extended range barometric pressure, okay? And here are the units right here. I just want to mention one thing. We are using random bytes for this data. So this MID says idle adjust system, and it's not necessarily in a real world scenario. This PID is probably not going to be matched with this MID, okay? But we don't error out. We just want to parse the data as it comes. There's a couple of other options I wanted to mention. So some people prefer JSON. We added a flag for JSON. I will disable the output that you just saw, which can be easily grepped. And I will print these messages in JSON format. And I'm also going to pipe the standard out to dev-no. Okay, so you can see in here, same messages, but these are output as JSON formatted messages. This could be convenient if you use the JQ tool and you want to filter these messages the way you'd wish. But there's another option for you, and that is we have a whitelist here. So what we can do is specify specific PIDs, like if we are interested in certain PIDs within a message, we only want to print those messages, we use the whitelist option. So I will just grab one from here and let it roll. So you can see it printed out one message with that PID, 48. And that is in actually decimal form for that. Okay, so there's a couple other things that this can do. If you just give it the -H, it'll give you some help. One of the options is for a custom database. Now, this means if you want to define your own messages and overwrite those that are provided by the spec, or let's say you're working with some proprietary messages and you have a good idea what it means, you can define that. We provide a sample file in the repo, and you can see here that basically this is the format. It's just JSON, and you just give it your definitions. You can use this file as a guide. Okay, there are still some issues. There are a few PIDs that are a little bit more tricky to work with, and those might not have their individual byte definitions overwritten, but it's a work in progress there. I wanted to mention that, okay, if you want to read from standard input, the way that you do it is you just pipe hexadecimal delimited bytes, as I mentioned, to this, and you will use this usual format for reading from standard input. Okay, I'll also use the I'll use packet delimiters here, and you can see what the meaning is. But one of my colleagues came to me and he said, well, you know what, we have an issue because the output that I'm getting from my program is not set up like that. It doesn't have the comma delimited values. It's all just a string of hexadecimal bytes. So what we did was we added the option here. If you look in this file called canon functions, an end user can define a function to be called on the command line that will manipulate this format. And the only requirement is that the output would be a Python list of bytes, okay, or a Python list of integers. So in this case, we can use the -J option and say canon no delims, I believe I called it. And you can see that it will just parse the message in that format. Okay, so it doesn't really matter. All you need to do is know what your input looks like and figure out how to get that into a Python list of integers. Let me see if there's anything else I wanted to mention. I think that's it for now. I'll let you guys play with the rest of those options as you see fit. So getting back, what are the benefits of using this decoder? Well, there's no real software investment other than getting your hands on the SAE specs. Okay, I'm sorry we can't just provide them for free, but SAE would not be happy with us, and they take the intellectual property very seriously. So I'm sorry about that. You could handle it, though, I'm sure. The other benefit is that you can work with anything that outputs 1708, 1587 messages. So where can you get it? If you want to get your hands on this tool, you'll go to this URL. After the talk, we will make this a public repo. We're rolling with an MIT license, so don't forget where it came from and feel free to make money on it. But remember that there are a few dependencies, so you need the specs, you need PDF to text tool, and Python 2 at the moment. We wanted to give a special thank you to NMFTA for giving us the opportunity to do this work, and our friendly motor freight carriers for allowing us to play with their trucks. Also the Hilton Executive Lounge for hosting a nice hacktacular atmosphere by letting this group meet and set up mobile test benches.
And we only left a few solder burns under nice wood grain tables.
We just want to thank you for joining us and enjoy the rest of your DEF CON talks.
All right, thanks a lot. If you have any more questions and answers, go ahead and make your way to CHV Track 2. Dan and Thomas are in there right now answering questions. We're going to have our next break is basically going to be for lunch, and at 2 p.m. Pacific, we'll have the next talk, Realistic Trends and Vulnerability Based on Hacking into Vehicles. All right. Have a good lunchtime. We'll be back at 2 p.m. Pacific.
one is available to take your call. Please leave a message after the tone. Hello? one is available to take your call. Please leave a message after the tone. Hello. Hello, no one is available to take your call. Please leave a message after the tone. Hello.
Okay, we're back. Next talk is Can Be Super Secure, Bit Smashing for the Win. Speaker is Brent Stone. He's an academic and professional cybersecurity researcher focused on helping average Joes get access to safe and reliable technology. His background includes work with statistical machine learning, search time series analysis, defensive cybersecurity, and industrial control systems. He has presented across the country from DEF CON in Las Vegas, IEEE in Chicago, and several other venues in between. I posted his Git repo link in the chat. That's going to be in track 2 text. Go ahead.
Hey, hello world. It's your boy Brent back with another talk on hacking cars. Last time we talked about how we automate the hack. This time we're going to talk about how to stop the hack automatically. So without further ado, this does not reflect any opinions of the government, the military, and any photos or cited papers that are shown in the talk. Those, of course, belong to their original copyright holder. And so let's talk about the threat. All right, so if we spoof the acceleration brakes and the parking assist to control the steering, we can get into a pretty dramatic situation where, let's say, a cyber criminal starts a three-way call with the mother. Their teenager is in the car. They say, "Mom, the car won't slow down." And all of a sudden there's a new strange voice, maybe a computer automated voice, says, "You have 3 minutes to send me $10,000 using the link in a text message I just sent you. If you don't comply, I will crash this car at 110 miles per hour." The attacker disconnects, leaving the scared mother on the line with their teenager who's about to possibly die from this exploit. This is not necessarily a fictional scenario. Surely you've probably heard of Chris Miller and Balasex's hack of the Jeep. So this is already something that's happened. And as cars get more and more automated, more and more connected to the internet, this is a threat that will continue to happen. So how do we stop it? Let's use offense. Offense is the best defense. We can specifically do bit smashing to stop the attacker in their tracks. What it turns out is actually, if you look at it, these control protocols that are in cars, while they may seem super insecure, with a very small and inexpensive change, we can achieve almost perfect security. And I'll get into that. Understand it's a very bold claim to make, but it's pretty surprising how elegant and well this defense method would work. So it'll stop your denial of service, which is typically thought to be unstoppable in these control network situations. It'll stop spoofing. And this will work for a lot of the control networks that are multicast, which means one sender sends a message and nearly all or all of the other devices on the network will receive that message. And the ones that it's not intended for will simply ignore it while it's on the wire. One other nice benefit of this, particularly for cars, is you no longer need an intrusion detection. It works out that the way that this defense is implemented, you achieve effectively perfect intrusion detection without any sort of complicated machine learning or AI. It just works. All right, so what is bit smashing? First of all, let's say Agent C on the network wants to send a payload of hex A, and they're the fraud. They're the attacker trying to send some malicious data on the network. Now they're sharing a physical wire with all of the other nodes in the vehicle or in the multicast control network. So B is our valiant hero who wants to stop this attack. So B wants to stop C in their tracks. What B will do is, while the voltage is still going up and down on the wire, as C tries to transmit their message, B in real time can stop that transmission while it's in progress by putting extra voltage on the wire that C is not expecting. And what this will do is essentially smash the logic that C is trying to send, and B will take over the communication on the bus. C will stop talking, and then the attack is stopped. So as you can see here on the left, C is sending 0, 1, 0, 1, 0. And by B sending that extra logical 1, that extra amount of voltage at a certain time segment, they effectively stop C in their tracks. So that's bit smashing. Now, I'm not the chef here, okay? Last time we talked, the previous talk called Reverse Engineering, 17 Cars in Under 10 Minutes. In that, I was a chef and your waiter. In here, I'm not the chef. I did not come up with this solution, and it's actually pretty well documented. In particular, this article you see in the green on the top right, that 2017 academic proof of concept, which was in the IEEE Vehicle magazine. I encourage you to grab a copy if you get a chance. Check it out. It's a very clear explanation of how the process works beyond what I'm talking about here. And then also they show you the hardware they use to actually implement this proof of concept. That way you can try this out yourself and tinker around without having to burn any sort of custom hardware. One part of this security that is not perfect is we're not getting confidentiality. Okay, this is still a control network. We're still basically talking in an open room where each person is a member of that room. And when they project their voice, no matter how loud you want to talk, you're not going to stop the fact that that other person is talking. Everyone else will still hear them. So you're not going to get confidentiality in an open room talking to other folks. But what we do get is integrity and availability. So integrity, am I sure who sent this message? Is the person I think it is? And then is this the message that they originally intended to send me? It hasn't been modified. There's no man in the middle business going on. And then for availability, that's your denial of service. Can I talk on the network when I want to talk on it? And is it behaving how it's designed? All right, so to give a little bit more context, we are not talking about general use networks. And here, I mean like the internet, Wi-Fi, anything where you can add or remove endpoints and adjust the structure and the number of participants in the network dynamically, and you don't need to make any adjustments, it just naturally works out. That's not what we're talking about here. We actually gain a lot of benefit by not having this, because here in the general use network, there's no way of necessarily knowing how many participants are on the network. So when you see new data go on the network, it's unclear whether they are a legitimate user and member of the network or not. Additionally, there's tons of metadata for keeping track of which messages are where, who owns what, and spoofing that metadata is just one more attack vector to make it even more confusing to know the origin of a message. But here we're talking about control networks, okay? So medical electronics, vehicles, obviously in this case, car hack village, but planes, trains, automobiles, factory floors, you name it. So control networks, you're not trying to add and remove hosts very often. You pretty much know the machines and components that you want to communicate, and that's a fairly fixed number. Maybe you might add one or two every couple of years, and you can document that. It's a very deliberate process. And you also lose metadata. And so in this case, it actually goes to our benefit here, because now there's even less information the attacker has to spoof. They basically have to talk in the wide open, and there's not a lot of extra information that they can lie about. They simply say, I'm this person, and send their information. And if there's already someone that says, hey, that's my name, so who are you? It becomes very clear and evident that that person is not who they say they are. That node is not legitimate. So what does this look like in practice? If A wants to send some information, they send it over the bus. Again, this is multicast, so everyone gets a copy. And if you look at this wiring harness from a vehicle, it might look something like this, where it originates at one point of that wire, and then it gets sent out to multiple other endpoints. Now, granted, in vehicles, there's a lot of things like gateways, which effectively create collision domains, or if this term is more familiar to you, subnets, even though it's not strictly subnetting. So sometimes these gateways, you don't necessarily see the entire bus on the vehicle. And we'll get to that, but that's not a problem. As a matter of fact, it actually goes to our benefit even more. So what is the problem? So because I have this multicast nature, and let's say I've got my instrument cluster talking to some other piece of information, I may also have a telematics unit. I may have a entertainment system that has a SIM card in it, where I pay for Wi-Fi connection to my vehicle. That way I have in-vehicle Wi-Fi. I can update my maps, whatever reason you want to be connected. Or for example, the Tesla business model, which is instead of having to recall vehicles, and it's a very expensive and time-consuming process, I can do a lot of things over-the-air software updates to change the behavior of the car, in which case a data connection is mandatory to do that. So again, we've got some sort of internet connectivity to the vehicle. Now these systems, which were designed to be pretty insecure, there's no cryptology, there's nothing, really no authentication, but it used to be air-gapped, so it was okay. Now it's no longer air-gapped. Now we've got attackers that can reach these networks. So let's assume the attacker has done so. One way or another, they've gotten onto our control network, and they can modify our brakes, they can turn off our accelerator, they can turn off whatever, possibly even take control if we have that power steering module, and we're in a lot of trouble. So we want to stop that from happening. One thing the attacker can choose to do, is a pretty dangerous attack, simply pick a high priority message identifier that no one else is using and just spam that as quickly as it possibly can. Essentially, you turn off all communications, and now you've got no steering, no acceleration, no brakes, you're just dead in the water. So if you look at the Wired article for when Miller and Balasek did the G-Pack, they probably did something similar to this. The other situation is a little bit more nuanced, is you've got a specific packet you want to send to a specific location to fool that part of the network, and you simply just say, I'm this person. And right now, the way it goes, even if B can see this happening, module B here, there's really nothing they can do about it. They just have to grin and bear it, that someone else is using their ID that they know should not be used by anyone else, and the attack simply happens. B can try to send messages all they want, but now you just get into basically DOSing the network all over again when you get into a fight of the legitimate B versus the attacker acting like they're B. So we want to stop denial of service, and we want to stop spoofing. So here's the solution. We're going to bit smash those communications. So again, bit smashing is adding that extra voltage on the wire, physical layer, in order to stop that communication or take it over. So the way we're going to focus on cars here, obviously because it's Car Hack Village, but again, this is fairly generic process, but here we've got the machine and its logic. So in this case, the actual physical brake caliper. There's going to be some internal wiring and control there to actually squeeze onto the disc brake and slow the car down. Okay, that's part of the machine and logic. The vast majority of the cost of that component is that machine and the logic. Touching that is what's called a CAN controller. Okay, that's a piece of little chip and or software within the bigger logical board that actually implements the controller area network protocol. So what order do I send things? How do I interpret messages? How do I synchronize with the network clock, etc. And then separate and distinct from that, once more, is the CAN transceiver. And that's the piece that actually implements the layer one electrical engineering to talk on the wire. Okay, so how do I actually make a waveform and create voltage on the wire to communicate? So in either case, I can leave alone all the design that I'm doing for my main machine, and I could just modify that commercial off-the-shelf product, that CAN controller or the CAN transceiver or both. If I modified one of those to implement bit smashing, then the manufacturer really doesn't have to care. They could just buy that product off the shelf, attach it to their existing product. There's really nothing else that they have to do, and you get the security. So it's extremely low cost. These CAN controllers and transceivers, we're talking less than $1 most of the time, if not pennies, to do this. And if we assume that that cost quadruples to add the bit smashing capability, we're talking about 20 cents versus 80 cents to get a completely secure solution. One way of thinking of this, if you have any background in security, is this is doing intrusion detection and prevention using a decentralized access control list. So if every endpoint knows what their name is, and they'll bit smash anyone else that tries to use that name, essentially you get an access control list. That way, stopping any sort of traffic does not pass that check. All right, so here I am, B, our hero, once more, good boy, and he's watching the bus. And I'm watching the attacker send some information. And the way I know he's an attacker is I'm watching him send bits on the bus over time, and I'm processing this in real time. I see that, hey, you just used my ID. That's not okay. Well, I'm the only one that gets to use that ID on this bus. So now I've got a long time, relatively speaking, to react and actually bit smash. There's about up to 80 or so, possibly even more, clock cycles or bus cycles, should I say, of the clock increments to have an opportunity to bit smash. So even if it takes a little bit of processing to actually decide, okay, yep, they use my ID, I'm going to use this clock cycle to figure out, yep, I definitely want to bit smash. And then in here, either the CRC or the data, I can just start holding the voltage high. I will bit smash that transmission. All of the members of the network will throw out that message, and they will even store it in memory. They won't even transmit it up to that higher component that they're supporting. Okay, it will stop at that CAN controller. So one time I just want to emphasize, if we're trying to say spoof or attack that brake, the brake won't even realize an attack is happening because it will stop at that controller chip or logic, and it won't even make it to the part of the control unit that's actually working the brake. It won't even realize it's happening. All right, so the way that would look, the telematics unit, if we say that's the source of the attack, tries to send a message. Before it even makes it to A, control module B, our hero, says 2 Bs. No way, not 2 Bs. There can only be one, okay? I'm the only B. We get this added benefit, okay, with CAN in particular. Anytime that an error occurs while you're trying to transmit, by the way controllers are supposed to be implemented to meet the CAN standard, if a fault happens while I'm trying to talk, I essentially get a hit against an internal counter that I have. We'll call that a fail state counter, saying something went wrong, possibly me, maybe I'm defective, and I'm going to keep track. All right, I'm going to try again. Well, as B continues to bit smash me when I use its ID, eventually I'm going to exceed that threshold, and I'm going to go into what's called a fail silent state, which essentially means that I will continue to listen to the network, but I will not send messages. And so if you're the attacker and you're trying to communicate with this car through the internet, and you've got some traffic and you're seeing the traffic go, even better is not only do I stop that attacker from physically being able to transmit on the bus, but the attacker may not even realize that they're stopped because they're still seeing the traffic come in, and they cannot necessarily get acknowledgements that their transmission was successful or not, depending on the logic between the machine and the controller that it's attached to. So the controller may or may not actually communicate that it's gone into a fail-safe state because it's failed. It's just not doing anything. So not only do we stop the attacks, whether that's denial of service or spoofing, but we've essentially done a DOS attack against the attacker's node and turned them off for some period of time. A couple assumptions to actually make this happen. So each endpoint needs to have a unique ID on this multicast network. So if you have multiple possible people using the same ID, then that's a problem. Because now it's unclear if I see that ID on the network, should I bit smash it or not? So every endpoint needs to have a unique ID. Gateways, okay, so if I have everything in my engine compartment, for example, going into a single gateway, and then that gateway talks to other parts of the vehicle, like brakes or something like that, or your tachometer, that essentially creates 2 different parts of the CAN bus, and nodes on either section may or may not be able to see traffic from each other. So now you've got back into the same situation. Well, if this node over on this section of the network is supposed to bit smash these IDs being generated on another section, but the gateway isn't forwarding that, it's not being a transparent, basically a bus instead of a switch, then how do I stop that? Well, you just reverse the logic. So if endpoint logic is, I'm going to allow all traffic except my ID. If I see my ID, I'm going to bit smash it. You flip-flop that logic for gateways. I'm only going to allow this set of IDs, and I'm going to bit smash anything that doesn't make sense. And that access control list, if you want to call it that, can be specific for each section of the network that it's physically connected to. What that allows you to do is, going back to the denial of service attack example, with CAN, I could just pick the highest priority arbitration ID possible according to the protocol. And more than likely, there's not going to be a device on the network that's using that ARB ID. So if the gateways weren't implementing this, then they would just be able to DOS the network. But by having these gateways, looking to say, I know what ARB IDs should exist, and you're using something that's outside of that list, I'm going to bit smash you. And then again, we go into, all right, now we've turned off the attacker's CAN controller. They can no longer talk. It's not a problem. And their message is never finished anyways. So the overhead imposed on the bus, it's really not that bad. And then finally, one talk, if you watch a lot of their talks that Miller and Balasek gave a couple years ago, is a lot of these ECUs, the nodes on a vehicle, will accept reprogramming commands while driving at freeway speeds. There's really no logic to check, should I be allowing a reprogram to happen or not? They just simply accept it. So one small tweak that would need to happen, either in the CAN controller or possibly that more expensive component, the piece is to add just a little bit of extra on that state machine to say, hey, I'm getting the signal, or I'm seeing that we're not in park, so I'm not going to allow a reprogram to happen. You need to put the vehicle in park before that happens. And then finally, we got to make sure that the controllers are just not rewritable chips. Okay, so that imposes some recall issues. If one of these transceivers starts bugging out, you will need to go back to the shop. But this basically makes it impossible, just like we wouldn't want to reprogram the logic for the larger component. If we have these very powerful bit smashing controllers or transceivers, we do not want to open up the opportunity for those to get reprogrammed and then used to just hold the bus high. And then there's really nothing anyone can do about it. You're just putting voltage on the wire, and there's no workaround for that. So we don't want them to be reroutable, but we do want them to continue to comply with that fail silent state. All CAN controllers should comply with that if they're compliant with the CAN protocol. And then again, other multicast protocols typically have similar fail states, but I'm not going to speak that I know for sure for every possible multicast ICS protocol. Thanks so much. Just again, references, if you want to look into this deeper, please check out the IEEE Vehicle Technology Magazine from 2017. Go ahead and grab a copy off of IEEE Explorer. And these guys did a pretty good job of really breaking it down and showing photos of how they created a working version of this without any sort of special hardware or production manufacturing capability. All right, with that, I'll open up to questions. Thank you.
Really? Oh, now it's not muted. I must have hit it twice. Well, I can do it again right now since it's not muted right now. So, all right. So, Q&A. We're going to keep that going in track 2 text. Next talk is going to be misbehavior detection for V2X communication. That will be at the top of the hour, and the Q&A will be in track 1 text. All right.
available to take your call. Please leave a message after the tone. Hello.